Welcome to today's Postgres conference webinar, Configuring PostgreSQL for Faster Analytic Query Performance. We're joined by Sebastian Dressler, Solutions Architect at Swarm64, who will discuss straightforward ways to get the best possible query performance from Postgres. Topics include configuring for parallel processing, HTAP approaches, fast analytic queries on transactional OLTP tables, PostgreSQL query acceleration extensions, and using replicas to scale OLAP performance. My name is Lindsay Hooper. I'm one of the Postgres conference organizers, and I'll be your moderator for this webinar. A little about your speaker. Sebastian has a wealth of experience in connecting hardware with software, building creative solutions. He's a solutions architect at Swarm64, helping customers fully understand how to fit Swarm64 technology into their environments. Sebastian holds an MSc from the TU Berlin in computer science, and NeoVim is his favorite editor. So with that, I'm going to hand it off to Sebastian. Take it away.
Thanks, Lindsay. Hi, everybody. Hope you can hear me well and see my screen that's already shared. And today's session is going to be more a terminal. So I didn't do any slides except for these textual slides here with my remote session on one of our servers. So we are going to also see a bit of action going on. And yeah, whenever I'm going to execute something on the machine, which is rather more in the end, during the end of the webinar, I'm going to tell you ahead, and then I'm going to show you a bit what I'm going to do and explain ahead so that nobody is lost. Okay, let's get started. Small introduction, Postgres and its natural habitat, so to speak. Well, we all know that Postgres is doing OLTP very well. And for those of you who saw yesterday's talk actually on SQL Server for Postgres users or vice versa, actually, you possibly noticed that there was one slide in there which is really interesting from DB Engine's ranking, where Postgres is overtaking more and more the commercial products and is becoming much more mature in the industry, actually, and also becomes, so to speak, the weapon of choice. And we at Swarm, we know this very well. And we also know that the OLTP functionality is really great and it's really robust and fast. But we, at the same time, see a bit of, yeah, I'm going to say shortcomings when it comes to OLAP. And this is actually where we are about to focus on and where this webinar is focused on as well. And turns out actually that you can teach Postgres to do OLAP really well if you consider a few things. And this is mostly the configuration in the end, which spans the typical good old costing system and also Parison these days, or actually starting since Postgres 10 and getting better and better since then. You want to have a bit of room to cache your data, or you want to go with partitions. And typically the schema you're using to represent your data should at the same time provide some guidance for your OLAP queries. So this is nothing new, because I mean, we all know that the schema is also essentially providing guidance for OLTP queries, but in that case, it's much more a question of ensuring constraints and ensuring data consistency. So we are taking this a bit and turn it slightly around. However, when like everything breaks, then given extensibility, Postgres, the Postgres community actually, better say, has a lot of great extensions which are there to help you. And then we are going to cover two of these today, plus obviously the Swarm extension, which I'm going through a bit more in depth and also then show you some examples. A bit of housekeeping, organization. So I try to break this down into 5 different parts. So we're starting a bit with config, and I'm going to talk a bit about the config. Then I'm trying to give you some recommendations on how you can improve your schema, make it a bit more ready for OLAP workloads, or even how you can consider putting OLAP and OLTP workloads together and then get what like Gartner coined as HTAP, which is becoming much more of interest now, and especially Postgres, we think, is the best tool in terms of open source tooling for that. After that, we are going to cover some query patterns. So I prepared 4 different coarse-grained topics around query patterns to give you an idea about what you can optimize, what you should look out for. And then we are quickly checking the extensions. And last not least, I'm giving you a demo with Swarm64 and 2 more OLAP queries, which are doing statistical computations on a data set we've chosen for this talk. And yeah, as Lindsay said, if you have any questions, feel free to post them in the chat. Lindsay is then going to forward them right away, and we can then answer them throughout the talk. All right, step number 1, get your config right. And I can talk days about config and about several parameters, and you all know this. You can go to the Postgres documentation, you can read through every parameter and then decide how I'm going to set this, or you can read one of the numerous blog posts out there covering configuration parameters, or just feel free to go to the wiki page of Postgres where they teach you basically the core best practices. However, when we are working with clients, we typically see kind of the top 3 pitfalls, and I want to share this with you to essentially, yeah, let's say, protect you a bit from doing the mistakes we then cover throughout very first calls we're having with clients. And number 1, basically, is actually my most favorite one, because there is quite a debate going on about this, how to configure this properly and how to not overload the system on the other hand, and this is parallelism. Now, parallelism is in Postgres starting slowly with 9.6, becoming better with 10, making a major leap with 11, and since then becoming even more better with 12 and 13. And I'm sure we are going to see much more improvements with 14. However, the key here is to configure your Postgres parallelism correctly. And it basically starts with those top 3 parameters. There is also some parameters for the costing system. I'm not going to necessarily cover them here because, yeah, this is something that is not so much of importance. Of course, it's important to get the costing system right, but getting the parallel configuration right is also very important. And our typical advice here is that you have to think in this terms of pooling, where your max worker processes is one pool and your max per workers is another pool. And then the one who really defines what's going to be driven to the system is the max per workers per gather. So they all depend on each other. And the rule of thumb here is set the 2 first ones really high, and then the 3rd one as needed. So basically, if you have a machine with, for instance, 24 virtual cores, then you can try to start setting the max per workers per gather to 24, right? Because that means if your query runs, it can make use of up to those 24 cores. Of course, it's important to note that this holds if you're running a single query. Now, if you're running multiple queries, dynamics changing a bit, and you maybe want to reduce this a bit. But yeah, this is the general direction. I'm going to cover in the next slide a bit more the debate around this setting here. And the one below is min parallel table scan size, which is something that is per default set to 8, which means it's we have to multiply this with 8 KB, because it's like the page size in Postgres, right? So multiply this with 8 because this is how many pages it needs to read. And this is typically too high. So the recommendation here is set this to 0. Start with 0, go test drive your query, see what's happening in terms of parallelism. If you get a parallel plan, great. If you get parallel plans across the bench, across all your queries, even better. And then you can take it from there and slowly increase the setting and start with 1 maybe or 2. Because honestly, if Postgres decides that the data is simply not enough to be queried in parallel because you have way too much overhead, then it's not going to do this. So this is just more really a helping thing, essentially.
We have a question.
Yeah, perfect. Thank you.
Of course. Jan asks, the upper limit for default statistics target is 2,000, isn't it?
No, that's 10,000 actually. Yeah, so exactly, right to the next point, default statistics target, 100 is the default, typically too low. I'm going to make the screen a bit bigger. I hope that helps. So 100 is typically too low. We recommend setting it to 2,500. Larger than that, you can try this. Typically doesn't yield too much of value. So this is a quarter of the upper limit of 10K. And yeah, this is something we really recommend, because if you have it to 100, then Postgres then starts to typically underestimate what you're having. Worst case, it will overestimate, and you just get off plans if that setting is not right. And don't forget to run vacuum analyze once you adjusted that setting. Same thing goes for sequential page cost and random page cost. The deal here now is that these are typically adjusted with respect to what your disks are doing, right? So if you have SSDs, for instance, which is like becoming more and more default storage, then one advice could be that you can reduce your random page cost. Why? Because it will then favor index scans more, especially those if you're having yeah, a lot of indexes, for instance, or if you have certain queries which would normally do rather a sequential scan. If you reduce the random page cost, you're getting more of those index scans, because it basically tells Postgres, hey, you can do scatter gather IO if you want. Like getting a random page isn't that costly. However, there's one pitfall here. You actually want to possibly do the opposite and increase random page cost. And sometimes it helps if you increase it to really extreme values, like sequential page cost is 1 and random page cost is maybe 16, 32, or even more extreme values. Why? Because the kind of, let's say, enemy of analytical queries are nested loops. Now, you can disable nested loops by setting enable nest loop to off, but you don't want to do this. Why? Because this is way more intrusive, right? So if you have, for instance, a UI tool like dbeaver, datagrip, or whatever, those are typically doing queries on your information schema to display the tables nicely for you in the UI. And those queries, they need nested loops. If they are not having the nested loops, they are going to take ages, and you're not going to like that. And the same holds for other queries, which really benefit from nested loops because there are not many rows to fetch, right? But on the other hand, you want to balance this. So in your journey of configuring Postgres, consider increasing random page cost. And even if it's just for a trial, right, it doesn't hurt, because Postgres is quite smart about this. And if it wants to use nested loops and random pages, it's going to use them. Number 3, work memory. This is typically quite off. The default is, if I'm not mistaken, 128 megabytes. And this is way too low for analytics, because if your query is doing a sort, for instance, then it's highly likely that that sort goes to disk, and that makes it slow. So you want to increase this. However, on the other hand, you don't want to increase this overly excessive. So the typical start, what we recommend, is a gigabyte to 4 gigabyte. So this would be like a conservative approach. Take the lower end, pick a gigabyte, run your query with explain, analyze, see whether it's going to disk actually or not. Because if it's not going to disk, the setting might be fine. If it's going to disk, increase the work mem a bit more. But don't overly increase it. Like, we have seen values of 24 gigabytes of work mem. This is just way too off, because there's like something that feels like a magical limit, which I personally suspect to be at around 12 gigabytes, something like that. And beyond that, nothing else changes. So the plan doesn't change, and Postgres is not consuming much more memory because this is more like a, let's say, upper limit for your workman, right? Yeah, I actually see a question in the chat with the, again, the 1 gigabyte to 4 gigabyte. It depends really on your RAM, right? So if you're short on RAM, rather go lower. There is another hint where we're coming to in the next slide. And I'm just going to switch to that slide now. And this slide talks about what I call the configuration controversy. And I just made this term up while I was writing the slide, right? So please don't nail me on it. If you're Googling that, I think you're not going to find anything. This is fresh from the top of my head. So the configuration controversy is the question about, is it okay to overutilize system resources? And I'm controversially saying, yes, it is, if you consider a few rules. And I'm going to cover this now, and then I'm also going to answer this 4 gigabyte question with the workman. So let's start with the CPU. Yes, this is okay, because your operating system actually knows how to share the CPU across multiple processes. So in nowadays systems, it's no surprise that you're running a couple of thousand processes at a time. Yes, they are not as demanding as a database query can be, but still, after all, the Postgres system is so robust that it easily can handle this. And we are having some benchmarks with DPCH, with the full 7 streams, where we, for instance, constrain the amount of concurrent queries to 5 with a workload manager. But those 5 streams are utilizing the whole machine with more workers than you would possibly want to configure. And that basically brings me also back to this max per workers per gather setting, because we typically set this to 54, as you see in the example below. However, and this is now circling back to the work memory, you want to watch out for your memory consumption, right? Because this is the one thing the operating system cannot share. So you either have memory or you don't. Maybe you have swap, but you don't want to use swap. That makes your system just really slow. And worst case, it becomes unusable. It becomes unusable to a degree where you can't even kill queries any longer. And then you will have a lot of angry people in your office. Now, sticking a bit more to this memory topic. So the point here is that a theoretical overutilization is totally fine. What means theoretical? Workmem is theoretical, right? Because there are 2 things here. Number one, workmem is kind of an upper limit, but at the second, like on the other hand, workmem is also giving you a planner hints, meaning if you have workmem that is too low, then your planner is going to, or the Postgres planner is going to adjust the plan accordingly to not overly exceed this kind of limit, right? If you increase the limit, then the Postgres planner becomes much more freedom. And for instance, a nested loop join turns into a hash join. Why? Because it assumes that it has enough memory. Now, this is unfortunately a bit away from reality, because just because you give it 4 gigabytes of planning room, so to speak, per worker, by the way, it's not going to necessarily use those 4 gigabytes. And that again circles back to the recommendation of start with, for instance, 1 gigabyte, see how your query is doing. Then you also have to adapt it to the circumstances where your system works in. It's like, how many queries do you run in parallel typically? And maybe you have to adjust it to that. But feel free to start with a higher value here and really try to drive the system to the limits, basically. And this configuration snippet I pasted in here, like those 4 lines, is something we typically use in our TPCH benchmarks. And you see we are really using 1,000 processes here, which is like a pool again, right? This is not meant that Postgres is going to use all these. It could, if you would allow it to, but we typically don't, because there are other measures in place, like what I said earlier. There is a workload manager, limiting it to 5 parallel streams. So the max you would get is something like 5 times 54 processes. The number of CPUs in the system here, because I see this question in the chat, is 64. Yeah, so this is roughly 75% of the system, a bit more. Now, if you do the math and you basically calculate the upper limit of peak RAM, and the formula is like you take the 4 GB times 54 workers times 2 nodes per query maximum, right? You can also assume 3, but 2 is a relatively safe bet. Then you get to 430 gigs of MEM peak utilization. But during the benchmark, this is not going to be exceeded at all. So our testing system has 384 gigs of RAM and the set 64 CPUs. But if you drive the benchmark through and you measure the RAM, you're going to see that this is way below the peak, and even if you run multiple streams. So WorkMem is kind of a safety net on one hand. On the other hand, it gives your planner freedom. So again, practical recommendation, depending, of course, on your RAM. What we would recommend with like the system of 380 gigs is go to 4 to 6 GB. That's typically a safe bet. If you don't really like this, then just lower it a bit more, but typically you don't want to go below a gigabyte, yeah, because that constrains your planner way too much. And what I said earlier as well, the 12 gigabytes here and everything beyond typically doesn't change much, right? So if you want, you can do this experiment. You just scale up your workmem stepwise. I don't know, for instance, 1 gigabyte, 2 gigabyte, 4, 6, and so on. And at some point, you will see that the plan stops changing. And that's basically the point where you don't need to go beyond, right? Because this is just what it is. Plus, running it once, maybe with explain analyze, to then really ensure, hey, my query is doing a sort not on the disk, but in memory, right? And what we typically see is people trying to do 24 gigabytes of workmem. This is just way off, right? Also, I haven't seen a practical case where this would work. Shared buffers, there we follow the rule, actually set it to roughly 25% of your main workmem. Again, you can do this in like a more experimental fashion, but the 25% are typically a really good choice. And also effective cache size, typically 75%. However, effective cache size is more a hint for the planner again. So it doesn't hurt to set this higher, especially let's say if you're using an extension like ours, then you can set effective cache size to possibly even the complete RAM, because the extension we provide is going to read from disk all times and not consume memory. So that's that. And let's move on. Next topic, schema practices for OLAP. And I divided this in roughly 3 parts: the good, the bad, and the ugly. And we start with the good things, of course. And the first good thing is it's totally okay to normalize your schema, right? So follow whatever normal form you like. 1, 2, 3, 5, 4, 5, 6. I think there are 6 or 7. I'm not so 100% sure. I think there are 6. At least I remember 6 somehow. The point about normalization is it helps you to reduce data. It helps you to get constraints in place, which ensure consistency across your data. And this is just a really good thing, especially if you're considering to merge OLTP and OLAP, then very likely your schema is normalized anyways. And that just really helps. And it also helps Postgres to do some better choices if you have queries across your tables, doing joins, and then schemas with constraints in place, they really help the planner. So this is a really important thing, that you get your constraints right. So meaning primary keys, unique keys, and foreign keys if you want to use them. So just get those right, and that will give you a happy planner, and a happy planner leads to a really good query execution. Pitfall: if you're using a lot of joins in your tables, then you should ensure that those columns you're joining on, that they are actually integer-based columns. Now, that doesn't mean that you're not allowed to use character columns, for instance, but be aware that if you have multiple of these and you're using multiple character columns in your joins, then the planner typically goes crazy. And that can lead to side effects which make your query slow in the end. Other extreme, it's also totally okay to not normalize. Why? You want not normalizing because it makes your query typically somewhat easier. So you can skip a few joins, for instance. It is like easier to write a SQL for that sometimes. And it's somewhat transporting a bit also this idea behind NoSQL, for instance, where you have everything inside one big document, even if you have to live with, let's say, null columns, or if you have columns which denote a specific type. So this is okay, typically not such a big problem for Postgres. And again, if you're using extensions which make your life in terms of reading from disk faster, then this is especially no problem. However, you also here want to have some guidance of constraints, meaning if you have columns which clearly have unique values, then mark those as unique. And the same is with indexes. People typically tend to have too many indexes sometimes because they think it's going to help a lot. But in fact, it's more a good practice to trying to reduce the amount of indexes, because that it's not only going to reduce the load in your database, but on the other hand, it's also reducing the freedom of the planner in that case, because if the planner has to consider too many indexes, your planning becomes slow, and there's a likelihood that you get a wrong plan basically in the end, or it's not a wrong plan, but the suboptimal plan basically. So in that case, you want to constrain the freedom a bit and try to reduce your indexes as much as possible. Going a bit about bad practices we've seen, or the already mentioned index hell. So like typical example that really happened, there was somebody doing a query, actually multiple queries on the schemas. It didn't really work, and then they just added indexes over indexes. And basically they looked at each query, seeing what kind of indexes does this query need, and then they just kept adding indexes. And that is, of course, increasing the amount of storage you need, but now maybe for most people, this is not a real problem because there's plenty of storage out there these days. However, again, you run into problems with the planner, and the planner is going crazy at some point, especially if you have chains of operations, like a lot of exists and not exists, or a lot of joins across the bench. Then at some point, the planner doesn't really know what to use in terms of indexes. In worst case, it will just do the wrong thing, right? Equally important, you have to really understand how indexes are picked, right? For instance, also something that really happened, this is possibly no surprise, the index definition is over 3 columns, A, B, and C. However, 1 out of 10 queries only need B and C. And this is clearly visible from an explain plan. So in that case, just drop that index, drop the index, recreate it over the columns the majority of queries need, and then that 1 out of 10 query where this would have been useful, maybe like that. Sorry, actually there's a typo here. Sorry, I'm fixing my slides right away. 9 out of 10 queries only need B and C. So that one query that's left over for that one, either you try to rewrite your query and then make it faster by that, or you just live with the fact that it's, for instance, doing a table scan. Yeah, and the table scan is not necessarily something bad. Depends on how you're scanning in the end, right? But if it's, for instance, a small table, then it doesn't hurt much. What really hurts is the other 9 queries that are running slow because of picking a wrong index or defining too many indexes. And I already talked about this in the good practices one. Again, this excess use of unconstrained non-integer based join keys. And again, example, this really happened. However, in that case, the person couldn't do much about it because this was very much UI driven. So the end user could create a schema and it would be created automatically. And most of the cases, the end user doesn't really care about what he's going to pick in terms of data types, nor was there a automated data type deduction in place, whatever. So that user ended up with a lot of text columns and really enormous amounts of joins spanning multiple of these columns. And now what happens is the following. The PG planner looks into your query, looks into your statistics, tries to get this fixed in terms for planning. And then at some point, and that magical point in this case, or at least that is what we have experienced there, was something about 3 columns. So the moment you went over 3 columns to be joined on, the planner just decided to, okay, I do the join for you, but after that, you will only get a single row. I'm going to tell you, you will only get a single row for that one. So everything else that follows upwards is based on nested loops. So you had a stack of nested loops. However, if you are joining, let's say, 10 million rows with 1 million rows, even if it's using many of those keys, then getting a single row out of that is very unlikely. And you just have to wait there and see how that system is idling on this stack of nested loops until it's done. And the only way to prevent that in that case is turn nested loops off, but you don't want this in your main config. You can do this on a per query basis, but hands away from the main config with nested loops. The obvious choice, obviously, would be to not use these text columns. But let's say if it's a date, then please use the timestamp. If it's an integer, please use the integer type and only use text if it's really a text.
Question here.
Yeah.
Text join key, is this acknowledged in their documentation or does it come out of experience only?
I think it's mostly an experience thing. We tried to Google this when this was happening. I think there's a thread somewhere, could be on the PG hackers list, where this is exactly discussed, but there's not really a workaround. And this was mentioned in yesterday's talk about SQL Server, because in that case, the customer was coming from SQL Server, by the way, and SQL Server is just way more forgiving on these things. Yeah, Postgres at the moment is not really. But there are ways to circumvent that by, for instance, hint, using a extension where the PG planner is somewhat improved. So for instance, I think Enterprise DB ePass does this. So there are certain extensions to the planner then where this is tried to be resolved. So this is somewhat known, but also not 100%. So there is a high chance that you stumble over this in practice, especially if you're having UI systems attached to your database where your users can go wild and create schemas at random. Now, last one, the ugly ones. Wasn't really sure, but yeah, I'm going to depict it like the ugly because it's like pick your poison a bit sometimes, right? Now, OLAP schemas typically don't include many constraints. If you have a raw OLAP schema, it could even be that you have no constraints at all. Why is that? Because you have a data source that is delivering your data into your database, and then you just trust that source that your data is correct, right? However, this is, again, pick your poison, right? Because this is making your database rather small. You don't have this excess of objects to manage your constraints. However, on the other hand, these constraints are really helpful as well, right? So again, rule of thumb here, if you have constraints which don't really add value, consider removing them. That could also be, by the way, foreign keys, right? I think I had a talk with somebody who told me when it came to implementation details, yeah, forget about foreign keys for now, focus on primary keys, unique keys, fully enough, right? Especially for OLAP when, again, you have a trusted source. However, on the other hand, add constraints as you need because they give you value, right? So If you have a unique column, please add a unique key to it. It will help the planner to create you a better plan. Second one, this combination again of OLTP and OLAP. There you are in kind of the other situation because you want to have constraints. Why? Because you have your OLTP tables in there, and this is not necessarily fed from a source that you are trusting. So if there's data coming in, you want to be told if you get a duplicate or if you have something mismatching in your foreign keys, whatever, right? So there they are absolutely necessary, and you don't want to strip them away. However, again, and this is now where this kind of, let's say, ugliness comes in, you want to try to remove certain constraints, again, if they don't bring you any value. So only keep the really necessary ones. And also, especially if you have additional constraints, or every additional constraints you bring into your OLTP table adds to or slows down your ingestion speed or any operation that needs to write, because you have to maintain these as well. Just another question, will PostgreSQL use foreign keys for query write and cardinality estimates? Yes, it does. And even if you have a look into the into the TPCH schema, then there are certain foreign keys defined. And on this one, by the way, it even helps if you put indexes on top. So that is another good practice, by the way, to speed up some of your queries in that case with additional indexes. So if you have foreign key constraints, consider putting some indexes on top. And you can even try this with primary keys. So normally primary key has an index already, but feel free to add one as well. Maybe not even the B-tree one, but if it's like a timestamp, then you can try totally with a Brin index. Partitions. Partitions are a good thing. They help Postgres to manage data better. However, when it comes to OLAP, you want to consider some things again. So you have to keep that feature of partition pruning in mind, right? Partition pruning is when Postgres knows which partition to pick from. And this is especially helpful if you want to reduce the data that is in motion, right? So that is especially useful if you have a constrained amount of RAM to be used for page caching, because this is when Postgres becomes really fast if your data is in RAM. The moment you need to read from disk, this is a whole other topic. So you want to try to keep your data in RAM all times. And to achieve this, use partition pruning. And for instance, partition over IDs or timestamps or categories, and consider to only use range or list partitioning, because that enables then partition pruning really. Hash partitioning also works with partition pruning. However, typically the hash function used to ingest into the separate partitions is doing that to generate a uniformly distributed data system, right? So meaning your data is spread across partitions, and in the worst case, you're going to read from all those partitions. Of course, you can put indexes on top again to make your reads faster, but the better choice here is to simply not touch a partition at all. So try to stay away from hashes here, but really focus more on ranges and lists. And also what we've seen, there is typically these days JITting on per default, which is a good thing because it makes certain operations simply faster since they are translated into code immediately. But for partitions, you want to maybe turn this off. Why? Because the JIT has to be done, or JITting has to be done for every single partition. If you have, let's say, 32, 64, 100 or 1,000 partitions or something like that, then you need to do the JITting for each of these partitions. And this is going to slow down everything. So if you're using partitions, consider JITting to be turned off. Okay, we made it to the query patterns. Again, I'm going to present you 4 query patterns. And the first one is a equivalency pattern where you can rewrite a not exist statement into a left join combined with is null. The point here is those two are doing the same job, typically they will result in the same plan as well, at least when they are like alone in the query. So like what you see in the example down here. However, if you're going to stack these, so you have multiple not exists, or that also works with exists, obviously. So if you have multiple of these, then there's a high chance that the planner is going crazy. And in that case, you really want to go to left joins and convert your stack of not exists into a stack of left joins. Or then, also with combination of is null, obviously, otherwise your not exists is not fulfilled. Or you can, of course, also do an inner join if you're doing an exists. I'm just going to demo this once. So let me run this explain plan. And I'm going to shift this to the right side. So you see this plan here. It's just like very straightforward plan. It's a parallel plan. We like parallel plans when we're doing OLAP. It actually uses a hash and anti-join here already. So this is what's happening behind the scenes. And I'm going to simply execute the explain on the other one as well. And as you see, nothing changed. Yeah. So planning time is roughly the same. And more importantly, the plan is the same. So and that's why you can transfer one into the other. However, when you're going to stack this, then the plan is going to change, and typically Postgres can do much better with joins than it can do with exists.
Hey, Sebastian, can you please define anti-join?
Right. An anti-join in this case is where Postgres swaps the orders, basically. So you see we have a rather big table here, the foo table with originally 1 million rows. It estimates 125,000. And the don't touch these table with rather few rows. I think it's 2,500, something like that. And in that case, Postgres just decides to swap the order, right? Because I'm telling it actually, please join, don't touch these to foo. And it's just turning this around. That's why it says anti-join here, because this is more efficient effectively. Next one. Favorite one of mine, actually, select count distinct. This is something really nice because it slows your queries down. And you want to rewrite this, and you have two options to do so. Either you do select count star and move the select distinct inside. And the other option is you do a select count star and you're not using distinct at all, but you're using a group by. Why I'm proposing this? Because by either of those two, you will likely get a more parallel plan. So I'm going to show this to you here. I'm going to execute all three of these. However, given my table structure, you won't see a parallel plan in the second one, but we can turn it into a parallel plan with some configuration trickery. It just means that the tables I created for this testing here, they are simply not big enough now. But let's start with the first one. So again, this is the classical thing. We want to rewrite. It does a aggregate and a scan. We don't like the scan because it's not a parallel one. So we want to have a parallel scan, please. Rewrite number one wasn't that effective. Reason here is that Postgres very likely did the right choice. I basically it decided against me, saying, okay, you know, I kind of know what you want from me, but I'm pretty sure this is the optimal thing here given the costing system. So we get the same, almost the same thing actually. It's just that, of course, you have to group somehow, and this grouping comes from the select distinct. The last one is a parallel one, and this is basically what we wanted. So if your tables are growing, try to rather formulate it as this last variant, right? And you see the cost here is much less actually. We are only here at the 6,500 versus these roughly around 17,000. If I add now the parallel tuple cost and set it to 0, which is, please don't do this, right? This is just for the sake of the experiment. Why? Because 0 is the most bad choice you can do. You're kind of forcing the system to always pick parallel plans. Sounds like a nice idea, but it isn't, believe me. But if I do this again here, you see here it's going to pick a parallel plan now. So we have the parallel workers here on the sequential scan, which is becoming parallel, and the cost reduced quite a bit. It's not as low as the last one, but it's showing you the right direction to go into. So if you're seeing select count distinct, consider to rewrite it in order to enable parallelism in Postgres. Pattern number 3, window functions. Also one of my favorites, actually. Why? Because window functions, unfortunately, are not parallelizable at the moment. Maybe that changes. I think there's some ideas around there in the community to change at least a few of them. However, given the nature of sequentialism in window functions, if you hit one of these and it has an order by, you want to pull the order by out. Why? Because if it does the order by outside the window function, it's going to be parallel. And this is, again, what we want, right? So you see already, I'm very much onto the parallel queries track here. So again, let's just look at the plans. Just doing this explain again. So here we have the window aggregate. You see it's doing the sort. The sort is sequential, and so is the scan. Rather high cost with 130,000 here. And now I'm going to just pull the order by out. So if you don't feel comfortable with this and you want to keep the order by in there, that's fine. You can do this. It's maybe going to sort a second time if it doesn't recognize that this is already sorted. However, even if it does sort a second time, then this will be faster than without the order by being external. In this case, we have only a single sort, and we didn't reduce the cost that much. That in this case is related because I have not the biggest table, right? And the sorting is not that expensive here as well. But if your tables are growing and you have, let's say, not even only a single sort column, but 2 or 3, then this is going to be extremely helpful. Pattern number 4, not really a pattern actually, but more, a statement that helps you a lot. And this is like the common table expressions, CTEs, or the with statement. So you're defining a with as something, write your query down, and then effectively you're creating kind of a temporary table, which you can reference later on in your next query, on the next part of the query. And that is increasing the readability of your SQL, and also helps to reduce redundancy, right? Because if you have like the same part in your query 3, 4, 5 times, you want to reduce this into 1. This is just a really good habit. Don't repeat yourself. So you are going to use a CTE most likely. CTEs are now inline since Postgres 12. What does that mean? Before Postgres 12, they were not. And this was a parallelism prohibitor. So most of the cases which used the CTE in Postgres 11, they hardly saw any parallelism except within the CTE itself, but everything else that used it was not parallel. Now with Postgres 12, that changed, obviously, and here we get parallelism again. The problem here is that there are some constraints. So CTEs are not allowed to have any side effects, which means if they somehow touch your data in another place, there's actually some examples in the documentation how this can happen, then the CTE is not going to be parallel again. And the rule of thumb in Postgres basically is the moment you have something which is not parallel in your plan, your whole plan is not going to be parallel. And this is really a core problem, right? So if you have, for some reason, a sequential scan that is not parallel for whatever reason, because your costing system is not allowing parallelism in that case, then nothing of your plan is going to be parallel. And reminder again on this min parallel table scan size, this is a very influential parameter on that one. If this is too high, quite often, even if your data set is quite big, you don't see any parallelism. And the same can happen with CTEs. So what to do with these? Just have a look into your explain plan. You don't even need to run explain analyze, just run explain without the analyze ones, see what it's doing, see how it's behaving. Do I have parallelism? Don't I have parallelism? And then decide accordingly. What to do with these? If in doubt, just create an unlocked table, right? CTE stands for common table expression. So in that case, just use a unlocked table. Does basically the same thing. Don't forget to drop it. Problem is, you're really tempted to do create table here, create temp table, pardon me. So if you can do this, because the nice thing about create temp table is the moment your connection goes away, the table is removed automatically because it's memory only, and yeah, then it will be gone. However, temp tables are also process local only, and they prohibit parallelism again. So please do not use create temp table for these kind of rewrites. You won't see any parallelism in the next query, and then you're basically back to square one. So really use create unlock table. And don't forget to drop it. Actually, a good tip for that is wrap it in a function, right? So wrap it in a function, and the function automatically does this, then does the dropping at the end for you. Okay, from query patterns to divide and conquer, I'm going to keep this a bit short. I want to still get the demo done and not take too much of your time. Divide and conquer, what's behind that? I think in one of the previous webinars, I used that term already again. So I'm just reusing it here now. If you have an OLTP Postgres and you want to put analytics on it, but let's say your machine is not strong enough to do that or to take the parallelism, or if your machine is already 100% utilized with the workload, really consider of applying replication. So get yourself a second instance with Postgres, follow the replication guide in the documentation, and then spread across the database. The best possible tip I can give you here is to utilize your logical replication, because that allows you to simply pick what you need. You could even apply early transformations, which then pre-shapes your data, maybe even combines tables together. So for going from a normalized schema to a denormalized one, and possibly making your life a bit easier. So this is a really cool thing, and hardware these days is rather cheap. So this is possibly a very good go-to variant. In addition to that, how to deal with much more data or with specific data, and now we are basically entering the land of extensions. And there are really great extensions out there, and extensions allow you to extend your Postgres, obviously, without forking it. And this is just, I think, the greatest invention since sliced bread with Postgres, right? Because this is so great. You don't have to go to a different product. You don't have to leave your ecosystem. You can just match it to your needs. One of these extensions is Citus. Citus provides you a horizontal scaling capability, and this is the choice if you have massive amounts of data you want to conquer with Postgres. And massive amounts can start already with a couple of terabytes. Typically starts not before, let's say, tens of terabytes or even petabytes. So this is something where you want to look into Citus, especially if you're having multiple nodes available. And again, these large amounts of data. The nice thing here is also you can, of course, combine it with other extensions. So if you have some extensions you're using, like the one below, PostgIS, then this is something that works together. PostgIS is more into going into this specific data extension direction, because it provides spatial data support and also algorithms to query that data, and then, for instance, to do clustering on data or routing, something like that. So you can do really fancy things with PostgIS, but I guess I'm preaching to the choir here. So these are two, and now we are coming closer to the demo. And the demo covers our extension. So Swarm64 DA. DA is for data accelerator. And the goal of this extension is to give Postgres more analytics performance. And we have a couple of key features. So we have a column store index, which definitely helps you with this index problem we just talked about earlier, because you could drop existing indexes and replace it by that one, and then drive your whole analytics over it. So that then provides a view onto existing tables, which Postgres stores in a row format, but you get by that a column-oriented storage without changing data, without copying data over. It just sits on top of your data and is even then maintained, which again enables these mixed OLTP, OLAP cases, these HTAP cases, because if new data is flowing into the system, then like any other index, the column store index is updated and stays up to date and gives you good query performance. We have a shuffle node. The shuffle node keeps the plan parallel. So if you have things like this distinct we talked earlier about, the shuffle node can detect this and then rewrites it automatically for you. So you don't have to go to this rewriting route I just told you about, but it will do this automatically for you. We have a process local join, which is a bit more optimized than the join that Postgres builds in. It's just optimized for this analytics case, right? Not necessarily for very tiny queries, then it also won't kick in because the costing system just works in Postgres, but for really big queries. And we have certain planner improvements. So this situation where I talked about previously, where you can get to this avalanche effect of creating a ton of nested loops, which you don't want, those planner improvements, they can prevent you from it. And I'm just going to show you this in like an A/B fashion. And for that, I prepared a data set, which we are actively working on. This is actually influenced by a client of ours, where we unfortunately don't get hold of the data itself, which would be great because it's a great data set, but we start to synthesize it and simulate it. And this data set is targeting loan applications. And you can just think of this as you have one person, the person X wants a loan, and then she or he goes to a website, applies, enters all the details you need for a loan application, and then automatically this is applied at 3 banks, possibly the ones where you have the highest chance to be successful with your application and where you get the lowest interest rate. And we simulate this basically and automatically apply it to these 3 banks. And then there is some, at the moment, very archaic algorithm which just decides based on the probability whether the loan is accepted or rejected. We can configure this. We can tell the data set of how many years of data to be generated. We can tell it how many applicants per hours we get. What we didn't teach it so far is that German banks are only open between 8 and 5 from Monday to Friday. So that's not in there. And that is also visible in the data, but that's something we're working on. So there will be some more realism, but for the sake of the example here and for the 2 queries I'm going to show you, this is more than enough actually. Schema looks like this. So you have basically a relatively straightforward schema still. The original one is way more involved. We broke it down a bit. And the main tables we are taking care of is this brokerage application and brokerage application request data. And then there are a few more sub-schemas, sub-tables actually. Also, for instance, covering economical data, like how much income does somebody have simulated, how many kids are there in the household, and so on and so forth. So you get the idea. We have a couple of constraints here. So the typical stuff, so basically nothing different from what I told you as best practices. We have primary keys, unique keys, and foreign keys. And we define some indexes. And the indexes here are optimized for the queries. So we have one column store index about over the biggest table we are having here, and a B2 index on top to get to not like make the query on native Postgres go worse than it could be. Sizes for this particular table, I'm only talking about this one because this is the only one we're querying basically. The other ones are rather small. It's 112 gigabytes plus indexes 10 and 15, and the column store index takes 52. On a partition table, the column store index works the same way. So you just define it across the master table, and then it's automatically pushed down to your child tables and gets created there. So if you query a child table, you will also see a column store index there. And this is then also maintained the same way. Okay, 2 queries I promised. Here are 2 queries. Number 1 is a naive Bayes classifier, which basically answers a question. And the question is, if I'm applying at a bank, depending on my income and whether I have additional income or not, am I going to be accepted or not? This query is inspired by a book I'm currently reading, Practical Statistics for Data Scientists. It covers a lot of R and Python examples, really very well readable. And I'm just going to run this query for you now. So, and the first thing, I'm just talking of complete Swarm. And we're going to run the explain analyze. It's quite an involved query. I'm just going to run this. And before I run this, I open HTAP. You see HTAP on the right. To just visualize a bit for you what is happening on the system so that you can see we are actually running in parallel, we are using a bit of RAM, maybe we are having some disk interaction and so on and so forth. And while I'm running this, I'm quickly going a bit over the query. So you see the query running now. And what this does is relatively straightforward. We have here the main meat in the query is down here, where we just query the income from this loan application table. We have to join together the economical data because the income is there. And we, for instance, don't want debt consolidations in here. Debt consolidation is when the person has multiple loans, she or he wants to consolidate into a single one, and we don't want this. So that's why we are doing this left join, checking that this is not null. And we see actually that the query came back. Fix that here. And just finishing the explanation, we push that then upwards, check the states with the income. So the final state must be either accepted or rejected. We define some arbitrary income groups. So these are based on German income values, basically between 50K and 100K, and then essentially calculating probabilities, right? And as you've seen above here, I'm using a with statement as well. So this with statement just gives me some probabilities, some key ones, how many percentage are accepted, how many are rejected. I can tell you this is like 75% accepted, 25% rejected throughout the bench, because the algorithm to calculate this is just not advanced enough yet in terms of realism. Right-hand side, we have a query plan. You see we have rather high cost here. This is 20 million, if I'm not mistaken. You see we get 8 workers in our CTE. This is run first, gets us 8 workers, really nice. And then down here is the other part of the query where the CTE is eventually applied. We get more workers. This is really good actually for Postgres because it will typically limit how many workers it applies on depending on the table size, and then it applies the logarithm. And we have a really nice parallel plan actually. So Postgres is doing really great, and in terms of speed, we are at 40 seconds here. Now, toggling on Swarm, and just rerunning the same thing again. I'm going to show you HTAP again, and just run it. And something died, so sorry, I'm not running it. And you see, well, first thing that's happening, you get way more parallelism. Yeah, that's something the extension does. It kind of lifts this limit I talked about earlier. So if you say 24 worker processes, you get 24 worker processes, no question asked. And that felt much more snappy. Sorry, a little bit struggling here. And I have to run again because I killed my window. That happens. Live demo effect, but we are not waiting too long. So this is ballpark roughly a 2x improvement. Yeah. Let's wait a second. There we go. And now you see a lot of stuff we put in. So we have here this output buffer, which is helping you on toolings like Tableau to make them go parallel because they don't typically. So then we have many more workers. We are having 24 here. This is how I configure the system. We see sort is happening in memory. That was the case before as well. And we see, again, a lot of parallel stuff. So this is a really nice query. 13 seconds. I think it was 39 before, if I'm not mistaken. So quite a bit of speed up. Really nice thing. Plus, because of the column store index, you get this more consistent because the thing is not relying on that things are cached. It just reads from disk, meaning you have to have beefy disks, but this is typically the case, plus it does compression. So if you're on Amazon, something like that, is not such a big problem in the end because of the compression. So you get a decent speed through that, and this is reliable. If I would drop the caches now, you would see that the query speed without any of the extension is going up through a minute or even more because it has to read everything from disk again, and that is unfortunately a bit slow. Next one, z-scores. I'm going to talk about the query while I run this because this is going to take a little bit longer. This is a z-scores query. I'm going to show you HTAP again. You see there is something running here, but this is it was shortly sequential. Now it's becoming parallel, which is a good sign already. You want to see this parallelism. We all love parallelism on our databases, and the z-scores actually they calculate exceptional things that might happen. So in this case, I took the time frame between when a application was received and the final decision was made, basically. And here it is then, or what the output of this is basically is it's telling you a score for such an event. And if this is beyond a certain limit, then you know this is kind of an outlier. So something must have happened there. Now, again, if I would have built in this thing, what I mentioned with the German banks, that they're only open from Monday to Fridays, then we would possibly get a lot of z-scores because you have a lot of piling up applications which are not worked on. And this is then an indicator for something where you get data points where you want to dig into a little bit more. For instance, it will tell you on this date, you have a z-score of 5. So meaning this was a rather exceptional long range between application received and application accepted or rejected, essentially. So this should be done in a moment. Takes about 2 minutes. When I measured last, the caches are filled. So this is quite the optimum already. And you see it's consuming RAM. So we are at 20% RAM here. Still room for improvement, right? So there's some tuning. You can add more queries. So at that rate with 20%, I would possibly not necessarily go beyond 4 or 5 queries running in parallel. Depends also a bit on what the queries they are running. Now we have the plan. And here, so we see it took 2 minutes, what I said. And here on the right-hand side, we have such a nested loop actually. And this is exactly the pattern we don't want to see. We don't want to have a nested loop in here because the table it queries on is rather big. It would be way more efficient to go in there with a hash and just completely avoid the nested loop. Switching on Swarm completely, showing you a HTAP again, this time not messing up with my windows, hopefully. I'm just running this again. And you see we get parallelism much more than before from the very beginning, which is a really good sign. By the way, this query is inspired by a blog post where the author teaches you how to do anomaly detection. And this is exactly what we're doing here. Really, really good read. URL is on the top. I can show you this in a moment. And of course, the slide deck is going to be shared. I'm going to upload this to GitHub tomorrow, and our query is done already. Haki Benita, by the way, is the author. Really good blog post. Go read it after the webinar. And we took 28 seconds. And 2 minutes down to 28 seconds. I think this is pretty awesome. And do we have a nested loop? No, we don't, right? And this is basically what the extension does for you. Everything put together, planner improvements, column store scan, the shuffle node, taking care that you are running parallel until the end, and then you get these kind of benefits. Okay, that's it. We are at the end. However, before you dash, one last thing. I actually wanted to put a Columbo here, but it's really hard to get a Columbo as ASCII art. You can barely recognize him. I see the question with the columns. I answer this in a moment. If you want to try Swarm, the Swarm extension, we have a free forever dev license. Just visit the website, get yourself one, try it out. It's available for Postgres 11 and 12 at the moment. And we cover the major Linux distributions, CentOS and Ubuntu, and soon enough Debian 10. If you need a Docker container, just approach us. We can also provide you one. If you're on AWS, there's a product called PG Nitrous, which is basically an EC2 AMI, which we are extending. So there will be many more features in future, also making it easier to replicate. Really good. And if you want to talk about your Postgres performance, then please feel free to approach me. We are offering you free of charge one-on-one session, talking about your performance and what kind of improvements you can do. So write me mail, and I'm happy to answer all your questions. Column store index, which columns did I use? The answer is pretty straightforward. You can use all of them. There's one constraint. You cannot use more than 32. So if you have more than 32 columns in your table, you have to constrain yourself a bit depending on what queries you do, or you create multiple column store indexes, which is an option. However, then your queries should not necessarily overlap, because then they are not going to be used. But rule of thumb is simply use all the columns you're having. And yeah, the table has 10 columns, so I used all the 10 columns basically. Then timescale. Timescale is supported to my best knowledge. I haven't tried so far the putting the column store index on timescale itself, but this is possibly also not necessarily needed, because timescale does a really good job on certain queries, and on all the other queries where it doesn't, we can help you with all the other features. So these features I just showed you, you can also, of course, switch them on and off as you want, right? So if you don't need the column store index because your tables are not big enough for that, maybe there's a certain size where it starts making sense, just don't use the column store index, but use everything else. That's timescale DB. Laravel, assuming you're referring to the PHP framework, yes, should work out of the box. As said, we are having some improvements. So we just released version 5.3, and version 5.3 features what you've possibly seen in the explain plan, what we call the S64DA output buffer. And that buffer helps you if you're using cursors. So normally in Postgres, stay away from cursors. If you're dealing with OLAP, then what happens is they are going to be sequential. And that's, of course, not something you want. However, with version 5.3, you are getting parallel cursors based on this output buffer. So yes, it works. I'm quite sure that it will also work with parallel queries. That's it. Now I talked a lot. I give it back to Lindsay.
That was a fantastic presentation and demo. And, I think it says a lot that our attendees were so active and into it. So that's always a good sign. So thank you so much, Sebastian. Wonderful, wonderful webinar. And thank you to all of our attendees, especially those of you who asked questions. So whether it's morning, noon, or night, wherever you are, I hope you have a great rest of your day, and I hope to see you on future webinars. Cheers.
Thanks a lot. Bye.